Now let's move into the mole and start understanding more about how we do some of our calculations for actual chemical reactions and what exactly we're getting when we weigh out a sample of some sort of a chemical. So the first thing to understand is this concept of counting by mass. So we have lots of items that we tend to group together. If I buy a dozen eggs, I know I have 12 of them. If I buy two 12 packs of cans, I have 24. If I have 12 packs of pencils, I have 144. Now paper though, okay, a ream of paper, 500 sheets. I don't necessarily want to count out 500 sheets, but what if I knew the mass of one sheet of paper? If I knew the mass of one sheet of paper and then I weighed out the entire package of paper, could I figure out if I actually have 500 sheets of paper? Okay. One of my hobbies is Lego. All right, let's say I bulk order a whole bunch of Lego off of Bricklink or something because I'm trying to do a huge original creation project. All right, I need a ton of bricks. So let's say I need 2,500 of these 2x4. Okay, so I need 2,500 of these 2x4 bricks. I make my order, I get my shipment. It's a lot of bricks. I don't necessarily want to sit there and count them all out. And the person that packaged them probably didn't count them all out either. They probably did something where, they massed out the amount of bricks. So let's say I get my bricks and I weigh out my package. And my package weighs 6,000 grams. Okay. Well, if an average brick of this size weighs 2.5 grams, I can take the mass of that and I can take the mass of one brick and I can figure out how many bricks I have. So I can say I have 6,000 grams times one brick in every 2.5 grams. Okay? This gives me 2,400 bricks. So did I get all of my bricks? No. In that shipment, I would not have gotten all of my bricks. Okay, medicines are done this way too. A pharmacist doesn't stand there and count out a ton of pills. Like let's say you're getting a prescription for 100 pills of something. A pharmacist isn't going to count out 100 pills. A pharmacist can do the same thing. A pharmacist, if they know, all right, well, one pill weighs this many grams, 100 pills weighs this many grams. All right, now I'm going to go on my balance and I'm going to dispense out the medication until I get to that mass. Okay, so how do we count atoms though? I can't necessarily sit there and count out individual atoms, all right? So we know some stuff on the periodic table. We know that I can look at the periodic table and I get these atomic mass units, okay? So one atomic or 1.0079 atomic mass units is one atom of hydrogen, or 40.078 atomic mass units is an atom of calcium. But let's say I weigh out 1.0079 grams of hydrogen. Well, how many atoms is that? What about calcium? What if I weigh out 40.078 grams of calcium? How many calcium atoms is that? And this brings us to our concept of the mole. Okay. So our mole is our base unit for the amount of a substance. And we compare back to carbon-12. There's a ton of carbon-12 out there. It's incredibly stable, so it's a great, baseline of comparison to. So it's the amount that contains a number of objects equal to the number of atoms in exactly 12 grams of carbon-12. And so we get this with our mole. It's the number of particles in the atomic mass in grams of an element. 6.022 times 10 to the 23rd particles. Okay, so 6.022 times 10 to the 23rd entities is equal to 1 mole. And this is known as Avogadro's number. Okay, so Avogadro's number we abbreviate with this N sub A here, Okay. And so we define 1 mole of a substance as exactly containing 6.022 times 10 to the 23rd entities. So if I have a mole of carbon-12, I have 6.022 times 10 to the 23rd carbon-12 atoms. If I have a mole of water, I have 6.022 times 10 to the 23rd molecules of water. If I have a mole of students, I am probably never sleeping again because I have 6.022 times 10 to the 23rd students, and that would be a lot of students. So this allows us to start, making these calculations. So when I have this mole, okay, I can also then have an equivalency on the periodic table. So a minute ago, I said, okay, well, if I have 1.0079 grams of hydrogen atoms, how many atoms do I have? Well, I actually have 6.022 times 10 to the 23rd because the masses on the periodic table are not just in AMU. They're in terms of grams per mole. So atomic mass equals at 1.0079, and I can express it in AMU or grams per. What I'm saying is that I have 1.0079 grams of hydrogen for every 1 mole of hydrogen. And if I have 1 mole of something, I have 6.022 times 10 to the 23rd of them. Okay, and so the thing when we look at the periodic table is everything has a different mass to it. So 1 gram of hydrogen is going to have a different number of particles than 1 gram of calcium because calcium has a molar mass of 40. Okay, so 1 gram of calcium is not going to be a whole mole. It's going to be about 1/40th of a mole, so fewer particles. And so we have to use the mole. We can mass things out in grams, because again, I'm not going to count individual atoms. If I can mass things out in grams, and then I can use some equivalencies with Avogadro's number and understanding this grams per mole, I can compare moles to moles because a mole of something is always going to have 6.022 times 10 to the 23rd entities. Okay, we can do this in other areas of life too. All right, so we know that a mole is this huge number. We also know that a dozen represents a number, right? 1 dozen is equal to 12 items. So let's first start thinking about this in more tangible, smaller numbers. So I've got an orange truck. It contains 5 dozen oranges. How many oranges are in the truck? Well, 5 dozen times 12 oranges in 1 dozen, okay, is going to give me 60 oranges. Okay, now let's think of something smaller. Sand. Sand is much smaller. So let's say that our sand truck contains 5 moles of sand. How many grains of sand is that? Now this is going to be a much bigger number. So I'm going to take 5 moles of sand. Now, Avogadro's number tells us that we have 6.022 times 10 to the 23rd entities of anything in 1 mole. So I can take my 5 moles of sand, do my 6.022 times 10 to the 23rd, and we're looking at grains of sand. So I have grains in every 1 mole. And so I end up with 3.011 times 10 to the 24th grains of sand. That's a lot of sand. Okay? All right, let's go back to our orange truck. Now our orange truck has a ton of oranges. 5.62 times 10 to the 7th. That is a lot of oranges. So how many moles is this? Well, now we're going to use it the other way. So I'm going to take 5.62 times 10 to the 7th oranges times 1 mole in 6.022 times 10 to the 23rd oranges. Okay. So now when you're doing something like this with a large exponent on your calculator, what you should do when you key this in is use parentheses. So like when I put this into my calculator, I do, and so the math here, this number, the 5.62 times 10 to the 7th times 1 over the 6.022 times 10 to the 23rd, the math is essentially just taking the 5.62 times 10 to the 7th divided by 6.022 times 10 to the 23rd. So when I punch this into my calculator, I do parentheses 5.62, and then I use the EE button because that EE button represents 10 to the, so I would do 5.62, I would hit the EE button, 7, close my parentheses, divided by 6.022 EE 23, close parentheses. And it's really important, if you don't enclose that 10 to the 23rd in parentheses, your calculator will read it wrong. What it'll do is it'll do 5.62 times 10 to the 7th divided by 6.022. And then once it's done that division, it will multiply the whole answer by 10 to the 23rd. And so numerically, you'll get the right number, but you won't get the right order of magnitude because instead of dividing by 10 to the 23rd, it'll multiply by 10 to the 23rd. So you need to make sure you put that into parentheses, okay? And so what you should get is 9.33 times 10 to the negative 17th moles. Okay, so you should get a really small number, which makes sense because you're dividing by 10 to the 23rd. So before moving on, grab your calculator, practice this, make sure that you can key this in and actually get the right order of magnitude, because if you can't, then you're going to have problems going forward as we continue to work with Avogadro's number. If you just can't figure your calculator out, come to office hour, email me, schedule a meeting with me, have your calculator on screen, and I'll walk you through seeing if we can get you to understand how to put things into your calculator. Because a lot of the errors that I see are related to punching things into the calculator wrong. So let's make sure that we can get our calculators worked out. All right. All right, now I have a bug truck with 5 moles of spiders. I don't like spiders, but this is an easy problem because it asks how many moles of spider legs are in the truck. So we need an additional piece of information here. How many legs does each spider have? Okay, so we have 8 legs per spider. Okay. And so this is similar to what we will start doing with chemical formulas, because I might be working with something that says something like H2O, and I might say, well, I have 5 moles of water. How many moles of hydrogen atoms do I have? And so then I have to use that 2 hydrogen in 1 H2O, just like we're going to use 8 legs in 1 spider with this problem. All right, so I have 5 moles of spiders. Times 6.022 times 10 to the 23rd spiders in every 1 mole. Okay. And then I need to know how many spider legs there. I have 8 legs in 1 spider. Okay. And so that'll tell me my total number of legs. Now, this is asking us, though, just for how many moles, not exactly how many legs. So, because we know that we have 8 legs per spider, okay, here's something else to think about. So, if I have 8 legs for every 1 spider, if I have 1 mole of spiders, I have 8 moles of legs. So, we're actually just going to do this. I'm going to do 5 moles of spiders times 8 moles of legs every 1 mole of spiders, okay? And that's how many moles we have. And then if we wanted to know the exact number of legs, we'd do that calculation right there. But we can take that understanding that in every one spider, I have 8 legs. So if I have a whole mole of spiders, I have 8 moles of legs for every 1 mole of spiders, which is a lot of spider legs, and I hope to never encounter that many spiders because spiders are evil. All right, so we end up with 40 moles of legs. Okay, now let's put this into practice with some actual elements. All right, so I have 4.21 moles of platinum. How many atoms do I have? So I take my 4.21 moles of platinum times 6.022 times 10 to the 23rd atoms of platinum in 1 mole. Okay, and I'm going to get 2.54 times 10 to the 24th atoms of platinum. Okay, so the next two go along the same line. So take a moment, practice these next two, and then unpause and I'll give you the final answer. All right, so let's see how you did. So for number 2, you should get 1.72 times 10 to the 23rd molecules of methane. And for the last one, you should get 3.0. I keep hitting the colors down toward the bottom. You should get 3.0 times 10 to the 23rd formula units of potassium bromide. Okay. If you didn't download the slides, I just realized this is how many formula units of potassium bromide are in 5.5 moles. And it's 0.50, so 2 sig figs, which is why we rounded this to 2 sig figs. Okay. So when we look at the periodic table, again, now we can think about those numbers either in AMU or in grams per mole. So silver has a mass on the periodic table of 107.9. So 1 mole of silver has a mass of 107.9 grams. So we say that silver's atomic mass is 107 grams per mole. Carbon, 12.01 grams per mole. Sulfur, 32.07 grams per mole. And so because there's an exact number of entities per mole, when we start making these comparisons and we start doing calculations, we can get to moles and we can start comparing between things because I have the same number of entities per mole. Okay, and so here's some of my relationships. So if I want to get mass, I take moles and I do grams over mole, so moles cancel out. Okay, so here, moles and moles would cancel. If I want moles, I take mass times mole over grams, so mass and mass cancels out. If I want number of entities, moles, entities over mole, so moles cancel. Or if I want moles, I take entities times mole over entities, so entities cancels out. Okay, and so that's how we set up these relationships. Now, if I want to start making some comparisons between things, and I start in grams, or I start in molecules or atoms, in order to then make comparisons between things, I have to convert to moles. So my center line here, okay, is in moles. So my ability to compare between two things, I have to go to moles. Okay? All right, so going forward for these, you will want a periodic table in front of you because we're going to start using a whole lot of numbers from the periodic table. Okay, so here's our first example, helium. I want to know how many moles of helium are in 6.46 grams of helium. So we want to go from grams of helium to moles of helium. Okay, and to go from grams to moles, we need the mass. Right, we need the molar mass. And since it's just an atom, I'll do atomic mass. Okay, and we get that from the periodic table. So I would do 6.46 grams of helium. And I look on the periodic table. My periodic table tells me helium is 4.003 grams per mole. So I get 6.46 grams of helium times 1 mole of helium in 4.003 grams of helium. So my grams and my grams would cancel out, and I am left with 1.61 moles of helium. Okay? So now zinc. I want to know how many grams of zinc we have in a certain number of moles. So here I'm going for moles of zinc, 2 grams of zinc. And again, I need that atomic mass. I look on the periodic table and it's 65.39 grams per mole. So I'm going to take my 0.356 moles of zinc. Okay, and I'm going to put grams on top this time. So I'm going to get 65.39 grams of zinc in every 1 mole of zinc. And we end up with 23.3 grams of zinc. Okay. Let's try one more. All right. So now I want to know what the mass of 1 silver atom is. So I need to go from atoms of silver to grams of silver. Now, I can't go directly from atoms to grams because what information do we have? Well, we have the molar mass. Our molar mass is in grams per mole. We also know Avogadro's number, which is entities per mole. The commonality between those is moles. So in order to do this, we have to go through moles. So our expanded roadmap here is we're going to go from atoms of silver to moles of silver. And we're going to go from moles of silver to grams of silver. Okay? To go from atoms to moles, we're going to need Avogadro's number. And then to go from moles to grams, we need that atomic mass. Okay? So 1 atom of silver times 1 mole of silver and 6.022 times 10 to the 23rd atoms silver. And then we look on the periodic table, it's 107.9 grams per mole. So then I get 107.9 grams of silver for every 1 mole of silver. Okay? All right. We should get a really small number for this one. Okay, so if you punch this into your calculator correctly, you should get a really small number. And indeed, you should get 1.79 times 10 to the negative 22nd grams. So 1 single atom of silver is going to weigh 1.79 times 10 to the negative 22nd grams. That's pretty small. Okay? So that's how we start dealing with moles and mass and Avogadro's number.